Yeah, and I'll be here for you when there's no one else. I see things been getting hard, you need somebody help. I'm really worried about the kids and tomorrow.
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So before I start showing you guys how to draw more MO energy diagrams, I wanted to point out 3 key points. So firstly, the average energy of bonding and antibonding molecular orbitals is approximately the same as the original atomic orbitals. Secondly, the greater the overlap of atomic orbitals, the greater the energy difference between the bonding and the antibonding molecular orbitals. And finally, atomic orbitals and sigma bonds have more overlap than pi bonds. So these are 3 points to keep into consideration as we look at these diatomic molecules. So first off, this is an example of a homonuclear diatomic molecule. What that means is that it's diatomic, meaning that there's 2 atoms combining to make a molecule, but it's homonuclear, meaning that they're the same. So examples of that would be O2, F2, B2, etc. If it was heteronuclear, it would be HF, for example, 2 different atoms. So MO energy diagrams result from quantum mechanical calculations. And for atoms with a nuclear charge of 8 and higher, so Z is greater than or equal to 8. And by nuclear charge, I mean that this is their atomic number. So any atom with an atomic number greater than 8 is going to have this setup. This is a typical setup for elements with atomic number greater than or equal to 8. So the energy levels of the molecular orbitals are like so. In this diagram, they don't show the 1s, so let me draw it out for you right here so as to not confuse you. So this is 1s, 1s, sigma 1s, sigma 1s antibonding. Okay, and so again, the energy is going to be increasing up as we go up in different orbitals, as you know from what we learned before. And so, as you can see, the sigma bonds are much lower in energy than the pi bonds, which we already knew. Okay, so let's do a practice. Let's do O2. So the oxygen electronic configuration is 1s2, 2s2, 2p2, 2p1, 2p1, because it has 2, 4, 6, 7, 8 electrons. So although this 2p1, 2p1 looks kind of funny, it's because there's x, y, and z p orbitals now. So I can also draw that on here where this is px, py, pz. Px, py, pz. Because remember, when we look at p orbitals, there's one in the x-plane, one in the z-plane, and one in the y-plane. Like so. So we're looking at these individual p orbitals. So oxygen has 8 electrons. So let's start filling it out on each side. So we have 1 atomic oxygen on the right, 1 atomic oxygen on the left. So we go 1, 2, 3, 4, 5, 6, 7, 8. So see, as you can see, we have 2 electrons in the 2 px, but then 1 in each of the other py and pz. We're going to do the same exact thing on the other side. 1, 2, 3, 4, 5, 6, 7, 8. So what does that mean? In the center, which is the molecule, O2, we're going to have 16 electrons. So let me fill this out for you. Remember, always fill out the lower energy orbitals first as you go up, and then also remember Hund's rule, where you don't want to pair up electrons until you have to. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. like so. So actually, the oxygen valence electron configuration, which I'm going to write right here, valence electron configuration, well, remember this is called the electron configuration, but atomic. So don't get mixed up between atomic electron configuration and valence electron configuration. So this can actually be written as sigma 1s2, sigma 2s2, sigma 2s star, because it's the antibonding. Basically, I'm going through each of these different levels and filling them up. So actually, I forgot the sigma 1s antibonding. And then we have sigma 2p x2. And then we have pi 2p4, pi star 2p. Okay, so as you can see, we just went through each of the steps, and I'm just showing you this because not only is it good to know it, but it's also getting familiarized with this different way of writing out the electron configuration, and it's really easy to follow when you actually look at your MO diagrams. So now looking at the MO diagram that we created for O2, using the number of electrons for one oxygen and the electrons for another oxygen, we can figure out a number of things. So the first thing we can do is bond order. Remember, we already did this before, so you guys should be familiar with this, and that is going to be 1/2 the number of bonding minus the number of antibonding. So for bonding, we have 2, 4, 6, 8, 10, minus antibonding, we have 2, 4, 6. And so you end up with a number 2. And this bond order makes sense, right? Because the way in which we find oxygen as a diatomic molecule is with a double bond in between. So yay, this worked out. Another thing we can look at is magnetic properties. So basically, when you have no unpaired electrons, this is called diamagnetic. So let me write that right here. Diamagnetic is no unpaired electrons. And on the other hand, there's paramagnetic, which means there's unpaired electrons. And so paramagnetic molecules are actually magnetic. They're attracted to a magnetic field, whereas diamagnetic molecules are repelled by a magnetic field due to the lack of unpaired electrons. So in this case, let's look at O2. We have 2 unpaired electrons right here. So which one will it be? It's going to be paramagnetic, meaning O2 is going to be attracted to a magnetic field. So again, by knowing how to calculate the bond order, knowing how to tell whether something is going to be magnetic or not, we can tell all of these things by just looking at this MO diagram. So this is just showing you how useful it is. So now let's move on to when we have an atomic number less than or equal to 8.
Destiny, nothing's coincidental, everything meant to be now.
I'm hoping that you're listening.
Just vibe with the most.